Welcome back, everyone. We're going to be looking at the remainder and factor theorem in 4.2 today. What is it used for? Well, we're going to take a look at its cases today. In this video, let's go ahead and take a look at these first two examples. It says here, find the remainder when you take a function and divide it by a factor. Or maybe not a factor so much, but maybe a binomial. So here's our binomial and here's our function. If you recall from division, let's just go ahead and do a pretty basic example. Let's say I do 17 divided by 3. When I do that, I can say that 3 goes into 17 5 times. When I get 5 times 3, that gives me 15. And then when I subtract, I get a remainder of 2. Now what do I do with that remainder of 2? Well, I can put that 2 over its divisor, which is 3. So I can say that's 5 2/3. Well, we're going to do something similar in polynomial form as well. So what we're going to do is we're going to treat the polynomial as if the coefficients are like the numbers themselves in like that number 17. So let's go ahead and take the coefficients. We have 1x cubed, 3x squared. Actually, let me write the variables above it. 1x cubed, 3x squared, 2x, and negative 1 is our constant. And we're dividing this by x plus 2. Now since x plus 2, if I set that equal to 0, I can see that x equals negative 2. So what I'm doing is trying to find that value of negative 2. So I'm going to go ahead and do a process called synthetic division, if you recall that from Algebra 2. What we do is we basically bring this 1 down, and then we're going to multiply this divisor by that number. So when we multiply, we're going to get negative 2. And then we go ahead and add these numbers together, and we get 1. We keep repeating that pattern. So negative 2 times 1 gives us negative 2. We add, and we get 0. Negative 2 times 0 gives us 0. And we add and get negative 1. So essentially, when we are dividing these, the polynomial, we're going to see that since we're doing x cubed divided by x, this is giving us an x squared. So this is our coefficient, 1x squared plus 1x. Then we have a constant here, so just plus 0. And then the remainder is what can be put as a fraction, minus 1 over the divisor, which was x plus 2. But more importantly, that's just the value of negative 1. I just want you to keep that in mind as we go on to the next step. When we do f of negative 2, let's go ahead and do it the old-fashioned way of plugging negative 2 into the function. So we're going to get negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 minus 1. When we simplify this, we're going to see that negative 2 cubed is going to give us negative 8. Negative 2 squared is 4, times 3 is 12, and minus 4 minus 1. So in the end, we're going to see that f of negative 2 is 4 minus 4 cancel out with 0, and we get negative 1. Okay. Let's go ahead and apply that same process over here. Let's see the connection that's to be made in letter B. Again, we're going to take our coefficients of x cubed, x squared, x. So what we see is that it's a 1x cubed plus 3x squared plus 2x minus 1. So I'm just taking my coefficients again, and this time I'm dividing it by, since x minus 1 equals 0, I can see that I'm dividing it by this value of 1. So I'm just going to go ahead and put a 1 there. I'm going to bring the 1 down. I multiply and add. I multiply and add. And I multiply and I add. Again, let's do the evaluated number, f of 1. So if I plug in 1, f of 1 is 1 cubed plus 3 times 1 squared plus 2 times 1 minus 1. When all is said and done, let's see what this simplifies to. 1 plus 3 is 4, and plus 2 minus 1, and that'll give us a value of 4, 6 minus 1 is 5. Okay, so the connection that I want you to make here, and this time I'll change the color, is to see how the remainder, negative 1, gives you the same as the evaluated number at that binomial's number, at x plus 2. we're basically evaluating at f of negative 2. The remainder gives you that same value. Over on letter B, notice the same thing. If we see x minus 1, we're looking for when x equals 1, and what you'll notice is that the remainder 5 is the exact same thing as the evaluated number. So that's the power of the remainder theorem. Let's go back a page, and let's discuss what the remainder theorem is. So I'm just right here at the bottom of this page here. So the remainder theorem, what is it used for? Basically, the remainder theorem, when you divide a polynomial by a binomial, let's go ahead and do that. When dividing a polynomial by a binomial, basically what we find is that the remainder is equivalent to the binomials evaluated value, like that. Okay, so as we go back to the previous page, or sorry, the next page, we'll see how that example again correlates. Right, again, I just want to make the emphasis here that when we divide our polynomial by the binomial, we get that evaluated number, the remainder, is the same as the evaluated number here. Okay, let's go ahead and apply that process here in number 2. Let's see how it might change, how we might give it a different name. Okay, so here we have a function, negative 2x cubed minus x squared plus 4x plus 3. Again, we're going to take the coefficients, so we have negative 2, negative 1, 4, and 3. And what we're going to do is, since x plus 1 equals 0, we can say what we're trying to do is find the value of negative 1. So let's go ahead and divide by negative 1 and do our synthetic division. We're going to bring the negative 2 down, multiply and add, multiply again and add, multiply negative 1 times 3, get negative 3, and notice how you actually get 0. It has a remainder of 0. Okay? If we do the evaluated value, f of negative 1, let's see what happens. You're going to get negative 2 times negative 1 cubed minus negative 1 squared plus 4 times negative 1 plus 3. So let's go ahead and find these numbers. What we see is negative 1 cubed is negative 1 times negative 2 is 2. Negative 1 squared is 1 minus, so we just get minus 1, minus 4 plus 3. So let's do that math there. 3 plus 3 is, wait, did I do that right? Hold on, 2, oh sorry, 2 minus 1 is 1, plus 3 is 4, minus 4, that'll give us our 0. And so you'll notice again that the remainder, 0, is the same as the evaluated value 0. Okay, let's do it again for letter B. So again, we're going to take the coefficients, negative 2, negative 1, 4, and 3, and we're dividing it by a value of 1. So let's divide by 1. Bring the negative 2 down and multiply. We add and multiply. We add and multiply. Did I do that right? Hold on, let me double check again. This doesn't look like it added up right. Bring the negative 2 down, we get negative 2. We added and got negative 3. 1 times negative 3 is negative 3. No, it looks right. We're multiplying 1 times 1 and we get 1. Oh, I see. And then we add and we get 4. Okay? So let's go ahead and make sure that this is right. If we plug in 1 into our function, we're going to get negative 2 times 1 cubed minus 1 squared plus 4 times 1 plus 3. When we simplify, we're going to get negative 2 minus 1 plus 4 plus 3, and that'll give us negative 3 plus 3. Those cancel. And yeah, indeed we get 4. The question that this problem was actually asking us is, when we use this theorem, we want to find out if these binomials are actually factors. What we notice is because we were not getting a remainder of 0, that means that it wasn't factored, right? Because if we think about how we divide numbers, if you end up getting a remainder, that's telling you that the number that you were dividing is not a factor of your divisor. That's why 3 is not a factor of 17, because you got a remainder. But if you end up getting something that does have a remainder of 0, let's say we do 3 going into 18 6 times, you'll notice you get a remainder of 0. When you get a remainder of 0, that's telling you, oh, 3 is a factor of that 18. Similarly here, going back to this question, since we got a remainder of 4, that's telling us that x minus 1 is not a factor of our polynomial. In the first example, we noticed that the remainder was 0, so what that's telling us is that x plus 1 is a factor of our polynomial. Okay, so basically, if you take a look at the process behind number 2 and number 1, it is using the same concept. They just give you different things. So you're still dividing a polynomial by a binomial, but now, let me change the colors now. When we actually discuss what the factor theorem is doing, we're still doing the same thing. We are dividing a polynomial by a binomial. And what we are now finding is that if the remainder is 0, then that means that the binomial is a factor. I apologize for all the background noise. I'm in the library right now. So when dividing a polynomial by a binomial, if the remainder is 0, then what it's telling us is that the binomial is a factor. If you think about what's happening graphically, what that basically means is if you were able to, let's take a look at the example up above actually. If you have a polynomial and you were able to divide it by a particular factor, then that means that it was a 0 on the graph. Because if the remainder is 0, that's telling you that the evaluated value is 0, and that means that it signifies it is on the x-axis of the graph. So that's the connection between the remainder and factor theorem. Okay? So I think I'll conclude this video here because this is just a video on the remainder and factor theorem.